Okay, this is chapter 24, capacitance and dielectrics. Okay, so I'm just going to open up. You need to know some formulas for capacitance. Okay, what is a capacitor? What does it mean? A capacitor is whenever you have two conductors and they're close together, they're separated by some space. That's what's called a capacitor. Okay, the first easy formula is capacitance is equal to Q over V. Q is charge, V is voltage. So the capacitance between two plates A and B, it's C is equal to Q over V, VAB. Okay, what's C? It's capacitance, and the unit is in capacitance in F, which stands for Farad. Okay, it comes from the English physicist Michael Faraday. Okay, so this is your formula, this is the unit. Okay, what should you know? For spheres, it's 4 pi capacitance is equal to 4 pi epsilon node d. I just need to make sure of this. Sorry, not d. It's for spheres. Whenever you have, remember, capacitance, you need two objects. All these formulas, by the way, you're gonna see most of them. You have VAB, RAB, whatever. So for spheres, RA and RB, it's 4 pi epsilon node RARB over RA minus RB. Okay, this is capacitance for spheres. For thin sheet, its capacitance is equal to charge potential over epsilon node. Okay, that's not an epsilon. Epsilon node like this. Or you could say there's another formula for it, which is what was it? One second, let me check it. But the one used mostly is actually this one over here, which is epsilon node A over D. Okay, so these are the main formulas you need to know. Okay, over here. Again, distance D is the distance between both capacitors. Okay, you need to know that epsilon node is a constant, which is 8.85 times 10 to the minus 12. Okay, let's start solving. A spherical capacitor is formed of two concentric spherical shells separated by vacuum. The inner sphere has a radius of 10 and the capacitance is 66.7 picofarads. Calculate the distance between the surfaces of the two spheres. So, what is we have spheres, right? Shells, whatever. What is the capacitance for a shell? Isn't C equal to 4 pi epsilon node RB over RA minus RB? Yes, it is. Okay, so this is our capacitance formula. Now, here they want the distance between the two spheres. Isn't the distance between the two spheres just the bigger radius minus the smaller radius? Yes. So we're trying to find out what this is. Now, we need to do that. We need to find what RB is, right? So we need to find out what RB is. We have the inner sphere has a radius of 10. So actually, let's find out what RA is. Let's call always, you're doing RA minus RB. Since we don't want our distance to be negative, let's make the smaller sphere as RB. Okay, so let's substitute all our values. C is equal to 4 pi. Epsilon node, sometimes it won't be given to you, so you need to have it memorized that this is the constant. But مثلا here, it's given. Okay, so don't count on it. RA, we said we're gonna call RA the bigger radius, we don't know what it is. RB is what? 10 centimeters. So let's make it 0.1 over RA, again we don't know it, minus 0.1. Now let's put our capacitance as 66.7 times 10 to the negative 12. Pico, P is pico, and it's 10 to the negative 12. Okay, solving this, let's do this. So 66.7 times 10 to the minus 12 is equal to 4 pi times 8.85 times 10 to the negative 12. Let me make this 85, sorry. Over here, times 10 to the negative 12 times RA, we're just going to call that X, times 0.1 over X minus 0.1. You get 0.12. So where did I go? So RA is 0.12 meters. Now, what is the distance between RA and RB? We know it's 0.1 meters. So what's the distance? Subtract these two, you get 0.02 meters. Okay, very easy. Okay, then they said if the potential difference between the two spheres is 200 volts, what is the magnitude of charge on each sphere? So now we have our capacitance. They gave us the potential difference, V. They want the charge, Q. What formula do we use? You have C, you have V, they want Q. We're going to use C is equal to Q over V. So obviously Q is going to be equal to CV. So you're going to get that 200 times the capacitance, which is what, 66.7 times 10 to the minus 12. Okay, and you get 1.334 times 10 to the negative 8. Let me check, is that correct? Yeah, 1.33 times 10 to the minus 8. Okay, very easy. Nothing too hard. All right. Question 2. When a potential difference of 175 volts is applied to the plates of a parallel plate capacitor, the plates carry a surface charge density of 35.0. What is the spacing between the two plates? So they gave us voltage and they gave us the charge density, which is this. Okay, what is the spacing? So they want the D. How do we do this? Now, I just want to fix this. This C here is wrong. It's not C. It's E. The electric field is equal to charge density over epsilon naught. Now, where does this formula come from? It actually comes from chapter 21, if you remember. We said for one sheet, the electric field is equal to charge density over epsilon naught, 2 epsilon naught. But if it's two sheets, you remove the 2, and it becomes charge density over epsilon naught. So that's what I meant here, sorry. Over here now, they gave you the voltage, they gave you charge density, they want the distance. Now I'm looking at the solution in the book, and they did this. Now you can just simply follow what they did here. They just said in the voltage is equal to electric field times the distance, and then electric field is charge density over epsilon naught, and they substituted it, and they got this. Okay, because E has another formula, which is V over D, and using the formula charge density over epsilon naught, equating these two, you can get that V is equal to charge density over epsilon naught times the distance. Okay, and then you can get this answer over here. Okay, to get the distance. It's not that hard, but how can I say? It's not that hard, but it's not easy. Okay, it's a lot of formulas you have to remember. Do I think this is gonna come? Wallah, again, I really have no idea. I've never done these exams before. I'm coming back from 1 month of leave. I've never seen this in my life. Okay, so then just substituting these values and you get this as your distance. Okay, you can pause and read if you want. Now, easy, nice, good question. A capacitor acquires a charge Q. What is the expression to calculate the capacitance? If you have Q and V, C is equal to Q over V. Very easy. The plates of a parallel plate capacitor are 3.54 millimeters apart and 4 meters squared in area. The permittivity, so they give you epsilon naught, calculate the capacitance. So capacitance, if you have area, distance, and epsilon naught, it's C is equal to epsilon naught A over D. Right, we wrote this over here. Okay, so sorry, I didn't write C equals here. Okay, so we wrote this here. C is equal to epsilon naught A over D. So simply just put everything in their units. This is the correct unit for epsilon naught. It's nice. The area is meter squared, but this, we don't like it. We don't like millimeters. So we have to change it to meters. Very easy. You get 10 to the minus 8 farads. Very easy. A 4 microfarad capacitor is connected across a 50 volt power supply. Find the charge stored in the capacitor. Again, C is equal to, capacitor is equal to charge over voltage. How do I know to use this? They gave me C, they gave me V, we want Q. Relate the two. C is equal to Q over V. Okay, so we're just gonna get 4 times 10 to the minus 6 is equal to the charge Q over the voltage 50. Multiplied, you're gonna get 2 times 10 to the negative 4, negative 3. Okay, 40, they said 4. So the course revision is wrong here. Okay, should be 4. If you use 40, obviously you'll get this answer, but here they said 4. Okay, find the equivalent capacitance in the following combination. So there's a rule for this. I'm gonna go read it and teach you guys. So I just read about it. For capacitance, it's the opposite to remember resistance. In resistance, in parallel, we would do 1 over R1 plus 1 over R2 and so on, right? And in series, we would just do R1 plus R2 and so on. But for capacitance, it's the complete opposite. For capacitance, you need to know in parallel C1 plus C2 and so on normally. But in series, you would take the reciprocal equals 1 over Cn. Okay, so then you'd have to flip it after getting your final answer. Please don't forget to flip at the end. So let's take a look here. We have all of these microfarads. Okay, so what's in parallel, what's in series? So in series, over here, you have this branch here. So I always like finding branch by branch. It's something that's worked with me all the time. So I'm going to find this branch here. They're right together in series. So how do I find it? It's going to be 1 over 2 plus 1 over 6, which is actually 3, 4 over 6. You're going to get 2 over 3 microfarads. Okay, but remember, after adding, you need to flip it. So it equals 3 over 2 microfarads. Okay, so add them and then take the reciprocal. So 1 over 2 plus 1 over 6, just so I show you on the calculator. Then flip it. Okay, you need to flip it. So 1 over that answer, you get 3 over 2. So 3 over 2 microfarads for this branch. Now how about the bottom branch? 1 over 4 plus 1 over 8. You get 3 over 8. Flipping it, you're going to get 8 over 3 microfarads. Okay, how about these two? Now, I'm not sure. Well, no. These aren't counted as the same branch. Okay, these 4 and 8, it's not as the same branch because as you can see here, these ones come back here. Okay, so it's not the same branch. So let's take a look. Now we found this branch, and this branch, right? So how do we add them? We have them in parallel, right? You have 3 over 2 over here, 4, and then 8 over 3. How do we add them up? If they're in parallel, we just add them up normally. Remember, if they're in parallel for capacitance, you have to add them up normally. Okay? So over here, you're going to get 49 over 6. So you get 49 over 6 microfarads for everything here. Now we still have this 8 here. Now, if you were to consider all of these branches and this 8, they would be in series together. So you have 49 over 6. Okay, and then you have this 8 over here. Now they're along the same line. This whole branch with this 8, they're together. So they're in series. So if I want to add them, am I going to do 49 over 6 plus 8? No. I'm going to do 1 over 49 over 6 plus 1 over 8 and then flip whatever answer I get. So 1 divided by answer plus 1 over 8. I get 97 over 392. So therefore, flipping it, we're going to get 392 over 97 microfarads. Okay, let's flip this. You get approximately 4.04. What's the answer they got? 4.04 microfarads. Okay. A 4 microfarad capacitor and a 16 microfarad capacitor are connected in series along a 50 volt supply line. The charged capacitors are disconnected from the line and from each other and then reconnected to each other with terminals of like signs together. Find the final charges Q1 and Q2 respectively. Now this is a good question, so you need to know this. So to do this, I'm actually going to take this into open board just so I can visualize how this looks. Okay, this question over here, a 4 microfarad capacitor and a 16 microfarad capacitor connected in series across a 50 volt supply line. Then they disconnected it and reconnected with like signs together. When you see like signs together, it means in parallel. Okay, find the final charges Q1 and Q2 respectively. So find the charges of Q1 and Q2 at the end. So I want you to understand what's going on. You have a capacitor here, 2 capacitors, right? They're in series. And then they connect them again, but in parallel. Okay, so we want to find the final charge Q1 and Q2 respectively. So here you have Q1 and here you have Q2. Then here you have Q1, here you have Q2. So we know that the capacitance here is 4 microfarads, and here you have 16 microfarads, and over here 4 microfarads, we have 16 microfarads. They gave us the voltage. We want to find charge. So we have capacitance, voltage, and we want Q. We know that C is equal to Q over V, so therefore Q is equal to CV. So over here, if we take a look at the total capacitance and the total charge, what's it going to be equal to? So let's call it C equivalent 1 and Q equivalent 1. Okay, what are they going to be? Okay, because we don't know what Q1 is, we don't know what Q2 is, but looking at them in total, we can find out what it is. We know that the voltage is still 50, right? Now, and why am I looking at equivalent? Because they gave me the voltage is 50. And voltage, did they give me voltage for any specific thing? No. They gave me voltage 50 means the whole thing is 50. So since I'm working with voltage the whole thing, I need to work with the whole thing for everything. So let's take a look at the total capacitance, so because we're working with the whole thing. So how do you look at the total capacitance? What do? You have 4 and 16. How do you add them when they're in series? You add them with the reciprocal method, right? So you do 1 over 4 plus 1 over 16. You get 5 over 16. Flipping it, you get 3.2 microfarads. So this is C equivalent 1. Now, charge. Here's the thing. Charge in series, it's the same for the whole thing. Okay, so if you have Q1 here, Q2 here, the rule is for charge, Q1 is equal to Q2. What's Q equivalent? It's the same thing as well. Why? Let me tell you why. Isn't current the same in all circuits? Yeah, sorry, so I got cut off. But like I was saying, Q1 will be equal to Q2, and that's going to be equal to the full circuit. Why? Because they're in series. Current, if you remember current is actually equal to Q divided by time, remember? Now, in series, in series, we agreed that current stays the same, right? So, if current 1 would be equal to current 2, equal to the full current in the circuit. Now, since current is the same, and time never changes, that means Q should also be the same, alright? So, that is the main idea. So in series, charge is the same. So Q equivalent in this case is going to be equal to Q1, which is going to be equal to Q2. So we can figure out what Q1 and Q2 is from here. But they want the final charges of Q1 and Q2 at the end after disconnecting and I don't know what. So let's take a look over here. Let's find first Q equivalent. So then we know what Q1 and Q2 is. We can substitute them here and here, right? Then we can substitute it here and here and find the charges here. Now, please pay attention, Q1 and Q2 here is not going to be the same as the Q1 and Q2 here exactly, okay? When I get there, I'll explain. But for now, let's find what Q equivalent is. So we now know the C equivalent, the total C here, the capacitance, we added them up, we got 3.2. We know voltage is 50, so we can easily do Q is equal to CV. 3.2 times 50. You get 160, right? So 160 times 10 to the minus 6, which is 1.6 times 10 to the minus 4 farads. Okay, why? Because this was micro, so I made it negative 6. Okay, so perfect. We now have our Q equivalent. Now, over here, this means Q1 is equal to 1.6 times 10 to the minus 4 farads, and Q2 is equal to 1.6 times 10 to the minus 4 farads. So we place it here, and we place it here. Now, Q total in this case will be Q1 plus Q2, right? صح? Why? Because now they're in parallel. So the total current is going to be different. Sorry, not current. Yeah, it's going to be different. But in this case, sorry, I'm talking about charge. So the total charge is going to be different. Since now they're in parallel. Here, they're equal. Same, and the total will be the same. But here, since they're in parallel, the total charge, now the charge will be additive. Remember when we used to have 2 amperes here, 3 amperes here? How do we find the total current? You do 2 plus 3 because they're in parallel. But here, they were in series. But here now when I made it parallel, I have to add them up. So Q total now in this case is not going to be this. It's not going to be 1.6 times 10 to the minus 4. It's going to be actually 1.6 times 10 to the minus 4 plus 1.6 times 10 to the minus 4, which gets you 3.2 times 10 to the minus 4. So this is your Q total. Now someone might ask me, Walid, why don't I put this as my answers? This is the charge flowing through the branch, right? This is the charge flowing through the branch. I want to know the charge of the capacitor, okay? So to find the charge of the capacitor, it's different, okay? You have to follow these steps, and this will most probably come in your exam, okay? So you have 3.2 times 10 to the minus 4. Now, this is our total. Now, we have this, our charge. We know the capacitance here is 4, and here it's 16. Now, can I find the volt? Can I find the voltage? Now, it would be stupid to find the voltage of this branch and this branch. And also, you can't, because you don't know the charge of this capacitor, and you don't know the charge of this capacitor. So, what are we going to do? We're going to look at them in total, right? So, let's look at it in total. In total, capacitance total, in this case, is 4 plus 16, 20 times 10 to the minus 6, which is just 2 times 10 to the minus 5 farads. Okay, why? Because they're in parallel, capacitance is added normally. Remember, it's opposite to resistance. So this is my total capacitance. So we have the total capacitance and we have the total charge. So using C is equal to Q over V, then we can easily find what the total voltage is. It's going to be Q over C, so it's going to be 3.2 times 10 to the minus 4 over 2 times 10 to the minus 5, which you get is 1.6 times 10, which is 16. Let me just check this. Yeah, so it's 16 volts. So we know that the total voltage is 16 volts. And since it's in parallel, that means you have 16 volts here, 16 volts here. Perfect. 16 and 16. Now we have the voltage of each branch. We have the capacitance of each branch. Can I now find the charge of each capacitor? Yes, I can. So we know that V1 is 16. Capacitance 1 is 4.0 microfarads. Can I find Q1? Of course. C is equal to Q over V. So Q1 will be equal to C1 V1, which is 16 times capacitance 1 is 4 times 10 to the minus 6. And then Q2 would be equal to C2 V2. Again, C2 is 16. V2 is also 16. So 16 times 16 to the negative 6 times 10 to the negative 6. Let's see what do we get. Did they get that here? Yes, they did. Okay, and these are the answers you're supposed to get. Moving on, question 8. Find the equivalent capacitance. See, like question 7 is a very long grid. But question 8, this is nice and easy. Find the equivalent capacitance. How do you do it if they're in series? You just add them, but with the reciprocal method, right? So you have to do this, and then flip it at the end. Right? It's very easy to do. 1 over 2 plus 1 over 4 plus 1 over 9. Let me just do it to demonstrate. 1 over 2 plus 1 over 4 plus 1 over 9. And then you flip it. You get 1.16. The 2SF, it's 1.2. Here, what's the equivalent capacitance? They're in parallel. So what do you do if they're in parallel? You add normally. So 2 plus 4 plus 9 is 15. They want it in, it's in micro. So obviously, normally it's going to be like this. Okay. Energy store. Okay, you know what? Let me just do it just so I can show you to make sure. You got here 15. But since it's in micro, your final answer multiplied by 10 to the negative 6. Okay? This is how you get the answer. Please don't forget the micro, the unit, the prefix counts. Okay, so 24.3, very easy. It's just formulas. You have capacitor of capacitance 25.0 microfarads has a charge of 12.5 microcoulombs. So they want you to find the stored energy, find the potential difference. So for stored energy, potential energy, it's U. Remember U? For U gravitational, U elastic, and now we have U electric. Okay, now electric potential energy stored in a capacitor. How do you do it? Very easy. It's Q squared over 2C, or half CV squared, or half QV. all of these formulas work depending on what you have given, right? So over here we have our charge and our capacitance given. So we're going to use U is equal to Q squared over 2C, right? Where is it? Q squared over 2C. Okay, so it's going to be the capacitor, sorry, the charge, which is 12.5 times 10 to the minus 6 squared over 2C, so 2 times 25 times 10 to the minus 6. And what do they get? They get this. You should get the same answer. Now, what's the potential difference across the capacitor? Now, we have our capacitance and we have our charge. They want us to find V. We easily, C is equal to Q over V, so V is equal to Q over C. And then you will get the answer over the 12.5 over 25, because the micro cancels with the micro. Question 11. The square plates of a 7.5 nanofarad capacitor measures 50 by 50 and are separated by a dielectric which is 0.25 thick. The voltage rating of the capacitor is 400, and they give us epsilon 0 is 8.85. What's the maximum energy that can be stored in the capacitor? Now, they want us to find U electric. How do we find it? What are our three formulas? Over here, Q squared over 2C, half CV squared, and half QV. Now, over here, when we say half CV squared, C is just equal to Q over V. So when you substitute Q over V into here, half Q over V squared cancels, so you get half QV. So that's actually how you get the third formula. Okay, anyways, three formulas, not that hard to memorize, صراحة. Half CV squared and half QV. Over here, what do we have given? We have the capacitance, we have the voltage, what else? We have the measurements, and they want this. They want the dielectric constant. Oh, whoa, sorry. I'm here. Question 11. I don't know what dielectric constant is. I'm still here. Okay. Same numbers, by the way, but they just added a different part in question 12. Anyway, so what is the maximum energy? So we want U electric. So we have the voltage, we have the capacitance. So we can easily just do half CV squared. Okay, let me just make sure I'm not making this up. Yeah, there you go. You see, all the other numbers are just Hebel. It's here, half CV squared. Okay, and you do half this times this times this. Nano, by the way, N is nano, and it's 10 to the minus 9. Okay, don't get this wrong. Very easy. Now, section 24.4 is about dielectrics. I won't be solving the top, obviously. We have three questions. Let me just read about this and I'll explain. So, dielectrics. What are dielectrics? It's so easy. So, we know that the capacitor is when you have these two metal plates beside each other and it does some stuff to the circuit, whatever. Now, if I went and placed a thin sheet, this is called the dielectric. Okay, this dielectric is placed and it helps because it actually increases the capacitance of the capacitor. Now, when I say it increases the capacitance, there's a rule you need to know. It increases by a factor K. Now, what is K? K is the dielectric constant. Dielectric constant. So, if you were to take a look at the capacitance, originally we said it's epsilon node A over D. Now, since it's increasing by a factor of K, the new capacitance, we're going to call this C0, the new capacitance after the dielectric is going to be K epsilon Z A over D. Very simple. Okay? Books call this K epsilon 0, they call it as just epsilon without the 0. See, there's no 0, it's just epsilon. So if you see this is also correct without the 0. But with the 0, it needs a K. Okay, so let's take a look here. They said find the dielectric constant of the device. So we have the capacitance. This is the new capacitance because they measured it. We can find the area and the distance very easy, right? Because they gave us the dimensions. So let's take a look. What's the area? It's 50 times 10 to the negative 3 squared, because it's a square, just do the side times side. And then the distance, it's 0.25 meters millimeters thick. So the distance is 0.25 times 10 to the minus 3. Okay, so let's substitute everything. Capacitance C nu, which is capacitance nu, 7.5 times 10 to the minus 9 equals K, which we don't know, we're trying to find the constant. Epsilon 0 is 8.85 times 10 to the minus 12 times the area, which is 50 times 10 to the minus 3 squared over the distance, which is 0.25 times 10 to the minus 3. Yeah, let's do it. 7.5 times 10 to the minus 9 times 0.25 times 10 to the minus 3 divided by 8.85 times 10 to the minus 12 times 50 times 10 to the minus 3 squared, and close the bracket. You get, this is your K, 84.7. Is that correct? Where am I? 84.7. There you go. Okay, calculate the dielectric strength of the device. So electric strength basically means electric field. Okay, now how do you find electric field if we have the voltage and distance? We did this in one of the previous questions, and it's actually E is equal to V times V is equal to electric field times the distance in between the two plates. You only use this rule when you have two plates. Okay, you need to know it, and it was in one of the previous questions. So how do you find electric field? Just V over D. Very simple. Okay, the voltage 400 divided by the distance between them. Very easy. Yeah, the solution is here if you want to see it. Type 13. A parallel plate capacitor has dimensions 1.5 by 5 and is separated by 1.4 thickness of bakelite of permittivity 4.9 and dielectric strength. So this is the permittivity is the constant yani. Okay, and dielectric strength, this is the electric field. The permittivity of free space they gave us epsilon 0. Sorry, relative permittivity is, hold up. Yeah, so relative permittivity, that is the K, like I said earlier. Okay, so what do you want? I want the capacitance of the device. Now, what do we have? We have the K, we have epsilon 0, we have the dimension, so we can find the area. We have the distance, so we can easily just do C is equal to K epsilon naught, because it's new. How do we know we're working with dielectric? How do we know we need to use this? Because we're saying relative permittivity. Okay, so that means you're working with this K. Okay, also they said they put bakelite in between the two plates, so K epsilon 0 A over D, right? So it's gonna be K 4.9, epsilon 0 is 8.85 times 10 to the minus 12 times the area 1.5 times 5, so 1.5 times 10 to the minus 2 times 5 times 10 to the minus 2, 0.5 times 10 to the minus 2 times 5 times 10 to the minus 2 over the distance, which is 1.4 times 10 to the minus 3. Now, putting this on your calculator, I'm not going to do this on my calculator. Is it here? Yes, I did it here. Okay, perfect. You get this. So that should be your capacitance. Now, what is the maximum energy that can be stored in the capacitor? So they want U. Now, what's U? It's half CV squared. We found what C is. Do we have the voltage? We don't. So we can use the other formula. If you remember, U is also equal to Q squared over 2C. Now, did they give us the charge? No, they didn't. They didn't give us shit. Okay, but so I'm seeing they gave us the strength, electric field. Now, let's see here. We can, with electric field and the distance, what can we find? We know V is equal to electric field times distance, right? So we can use that here to find the velocity, to find the voltage, and plug it in over here. So V is equal to electric field 2.4 times 10 to the 7 times the distance 1.4 times 10 to the minus 3. Very easy. So you can just use a calculator. 0.4 times 10 to the minus 3, you get 33600. Okay, volts. Now since you have the voltage, you can easily use half CV squared. So half times C we found is, where is it? This, we got this 2.32 times 10 to the minus 11. And then V is going to be 33600 square. Is this correct? Yeah. So you get this answer. Next, question 14. A student wants to create a simple capacitor using aluminum foilless plates. The student cuts two pieces of foil having these dimensions and separates them by a distance of 2. Which of the dielectric constants, K, be such that the material produces 1.0 nanofarad capacitor? Okay, so this is very easy. وكمان they give us epsilon 0. They're telling us to use this as E0. طيب, so they give us the capacitance. They want us to find K. And we have E0. We have the distance, and we can find the area. So how do we do this? Which formula has C, E0, K, and D? C is equal to K, epsilon 0, A by D. Right, so let's find it. K is just K with one moment. Epsilon 0, they told us to use this. So use this, huh? The area is 0.15 times 0.08 over the distance 0.002. On your calculator, you get what? Oh yeah, when you find K, sorry, this should all be equal to your capacitance 1. So 1 times 10 to the minus 9, because it's nano. Okay, so over here you get, yeah, so 1 times 10 to the minus 9 times 0.02 divided by 8.8 divided by 0.15. Yeah, okay, perfect. That should get 19. Okay, هيك نكون خلصنا. I'm not doing question 15. Tops are not included. Thank you so much for watching, and good luck in your exam.